All right, talking about trapezoids. Okay, this is another type of quadrilateral. Okay, the key word here, though, when we create this definition, is that it has exactly one pair of parallel sides, and this is all about how we interpret what we mean when we say something. So for instance, let me write this phrase down. What if I wrote? Would you agree with it? Would you say that this is true? A parallelogram has a pair of parallel sides. Would you agree with that? Okay. Hopefully you agree with that because it has two pairs of parallel sides, right? Okay. So if I just write this definition that way, obviously, this word here, A, numerically could mean 1 to us, right? So would you agree that a parallelogram has one pair of parallel sides? It would be exactly the same thing as saying a parallelogram has a pair of parallel sides, right? So if I define my trapezoid carelessly as a quadrilateral with one pair of parallel sides, the way we interpret that is that when we say one pair of parallel sides, we're saying that's a bare minimum. Okay? So we're saying that it could have two parallel sides. And if it could have two parallel sides, or pairs of sides, then it becomes a parallelogram, right? So by carelessly defining my quadrilateral, I could accidentally, not on purpose, but accidentally, construct a definition that classifies some parallelograms as trapezoids. Does that make sense? And we don't want that to happen. So the way we construct the definition so that doesn't happen is that we put that word exactly in it. Okay? And now there's no ambiguity in regards to how many are they talking about. Are they talking about one pair of parallel sides? Are they talking about the potential of having two pairs of parallel sides? Here, there's no ambiguity. There's no question, right? There's no confusion. It's exactly one set. Okay? The parallel sides we refer to as bases. Okay? The key thing here is that when people think about the word base, just the normal kind of thought or positioning is, for instance, if I say think about the base of your desk, where do you think? What are you thinking about? What part of it? Towards the bottom, right? Okay. Bases don't have to be based or positioned in regards to their location of up and down, okay, or top and bottom. Okay. Bases can be top and bottom, but they can also be left and right segments. Any one of those, that trapezoid, that tan trapezoid, would you agree it's a trapezoid in that position, right? And it has a top and a bottom, but it is also a trapezoid in that position, right? And now maybe you question whether there's a top and a bottom, correct? Okay. So we need to be able to have words that allow us to still talk about the parallel sides of that shape. Okay, and it's just a little bit easier to just call them bases. Okay, instead of say, hey, look at the parallel sides. Now I just say, look at the bases. It's easier to say. The non-parallel sides are what we refer to as legs. Okay, and if you remember back to dealing with triangles, there was a series of triangles. There's going to be some more we come up with here in the next couple of weeks. There was a series of triangles that had bases and legs, right? An isosceles triangle had bases, or base angles, or had a base segment as well, and it also had legs. Okay, so there's some common terminology here. So it's probably good that we say base of a trapezoid and legs of a trapezoid, so that in common conversation, I say base or I say legs, we're all on the same page in what shape we're talking about. Okay, is that doable? Now those are some just vocabulary words, so we're going to start using those, but you need to convince yourself of that stuff by tomorrow. We'll start talking about them on a regular basis. Here we've got another vocab word. Basically what happens is in the structure of all these quadrilaterals in our diagram or categorizing like flow chart, we get to a trapezoid location, and then we can better classify some trapezoids. Some trapezoids can be referred to as being isosceles. Okay? And the word isosceles, every time you hear that word in a math class, is going to bring up the same concept over and over again. Okay, I'm not going to hear isosceles in chapter 3, and then isosceles means something different in chapter 4, and means something different in chapter 7. Okay, isosceles early on meant two congruent segments, right? Two congruent legs. When we talk about isosceles trapezoids, it means you have two congruent legs. Okay, so that's a picture of an isosceles trapezoid, and they're all going to look that way. They're all going to look like the legs are kind of like sprawled out from one another, and they're going to converge at the top, and that can be reflected and upside down, all that kind of stuff. But what I'm trying to say is this leg here, for trapezoids, that leg can move. So let me see if I can get a picture here. Let's go. Bless you. Don't do it again. Kidding. All right, so we got a trapezoid here, right? Okay. Hopefully you realize, the top and bottom, they're parallel, right? Okay, they're both horizontal in this case. If I look at these slopes, those two slopes are different. That's that slope there and that slope there, right? Meaning that they converge. Now, if I can get the lengths of these two things to be the same, so let's put the lengths in here. That length of 2.48 and that length of 2.23. Let's say that I'm able to get those to be the same. So let's see here. Pull that point out, pull that point out. So now we've got slopes that are still different, right? -2, 2, they're different. But now these two things are equal, correct? Okay. I can make this segment here kind of change its direction, make it a slope of 2, so that's still 2.23. Does that make sense? Okay, so this is an isosceles trapezoid, but I can do, and actually I'm going to have to do it, I think, maybe with this one. Yeah. I can take that point and start moving it in here. Now, it does adjust D just the way I've created it, but hopefully you realize eventually, if I were to get D, I think I kind of created this kind of messed up. Let's see if I can force D to fix there. I want D to move. I guess the animated version of this isn't going to work real well because that D is moving for some reason off of B. But you can see, hopefully, that if I take AD and start moving A so it came this way, that the segment AD would turn into that segment, right? And now, what is that shape there? It's a parallelogram. Okay? So, and when I do that, the reason that becomes a parallelogram is because now we have created an isosceles triangle over here. Okay? Because that segment is the same as that segment, right? And that angle right there is congruent to that angle. Okay? In regards to the trapezoid here, okay, this blue angle down here was supplementary to that one, okay? So that blue angle is now here, and that's going to be supplementary to that one, meaning to us eventually that this angle here, I'm not going to work through all the algebra here with you in the proof of this, but we eventually figure out that those two angles are going to be supplementary. Okay? And that occurs essentially one reason because of the parallel lines up top. And we can kind of work through here and figure out if those are supplementary, this angle here is going to be supplementary. Okay? And that creates that line there to be parallel to that line. Okay? So, in the whole grand scheme of things, when you're dealing with an isosceles trapezoid, okay, those two legs have to be they're going to be opposite slopes. Does that make sense? One was positive 2, the other one was negative 2. Okay. Where this is still, if I look at that shape, that is still a trapezoid. Does that make sense? That is still a trapezoid. Okay? Because that slope right there and that slope right there are different slopes. Okay? But the top and the bottom are parallel, right? So one set of parallel lines. It's starting to look more trapezoidal, or sorry, parallelogram-like, right? Okay? But it's still a trapezoid. That is still a trapezoid. But once I get it to be something like that, now it's a parallelogram, right? Okay? So when you're dealing with an isosceles trapezoid, that's kind of the general image that you're always going to get. Okay? No, because to be a parallelogram, those two sides need to be congruent and parallel. And in this case, they're just congruent, right? They are going to converge eventually when I extend those. So, maybe a longer discussion than necessary, but every time you deal with an isosceles trapezoid, it's going to be that picture. Okay, it's something similar to that. What we learned in regards to, and we can prove this, and I actually got you proving this, or have you proving this in a question in your homework to see if you can remember stuff with congruent triangles. So I'm gonna kind of just give you the theorem today and see if we can work through the proof this evening for homework. But what we learned is that both pairs of what we call base angles in an isosceles trapezoid are congruent. Okay. If I deal with this segment here and that segment there, those are my legs, right? So this is a base up here, and this is a base down here. Okay? So what we end up with is a set of angles that are congruent. We have angle 1 and angle 2. Those are a grouping of base angles. And do they look congruent to one another? Yeah. In regards to maybe comparing 3 and 4, 1 looks congruent to 2. 1 does not look congruent to 3, right? 1 looks like an acute angle, 3 looks like an obtuse angle, right? Now, I know we don't want to go off looks, but this is one set of base angles. And 1 and 2, those two angles are congruent. That's going to be the case in regardless of any isosceles trapezoid that you deal with. If I look at 3 and 4, what's the relationship that you think you would see with 3 and 4? They're base angles again, so they're going to be congruent. Is that all right? Okay. So when you say in an isosceles trapezoid that base angles are congruent, you're actually saying that you have two pairings of angles. Okay. You got the blue angles here, and you got the red angles. Okay. Now we'll never compare angle 1 and angle 3 in regards to congruency, but angle 1 and angle 3 should be what's going on? Supplementary. If we've got that line there and that line there, and by definition of this thing being a trapezoid, those lines are parallel, right? And then I look at that transversal, that angle there, same side interior angles, aren't they? And same side interior angles have to be supplementary if the lines are parallel. All right. So just some properties that, like I said, in your homework this evening, you're going to work through this proof. It's got drop-down windows and stuff like that. They guide you through it, so it's not all by yourself. And we'll talk about that a little bit more tomorrow. This is an additional theorem, okay, which additionally you're going to prove again in your homework tonight, so I don't want to go through the proof right now. But it says if a quadrilateral is an isosceles trapezoid. The key thing here is that it's not just saying trapezoid, right? It's saying isosceles trapezoid. Okay? So this is not true for all trapezoids, it's just true for isosceles ones. Okay? It says the diagonals are congruent. If you have an isosceles trapezoid, the diagonals are congruent. Okay? And now I think we've done enough throughout this year that when we had a theorem or a property that says these two shapes or these two segments are always congruent, then the questions that they provide you in homework are, maybe BD in that picture is some algebraic expression. And then AC is some algebraic expression. And they ask you to solve for X or Y or Z or whatever the variables are in those algebraic expressions. Here, you would just take BD equal AC, right? Okay? So I think we're getting to the stage in the course where we've done that enough. We've done that for 3-4 months now with different properties. And as we start going through and start seeing properties or theorems that state a congruency, I'm not going to spend a whole lot of time in class talking about examples of how to do those types of questions because they're very similar to other aspects of the course. Does that kind of make sense and why I do that? I think we're spinning our wheels and kind of wasting time going over that same procedure over and over and over again. Okay? If you learn the theorem, you learn that relationship, I think you guys can set things equal to each other. Okay? The diagonals in an isosceles triangle are indeed congruent. Okay? But that is not the case for all trapezoids. So let's go back to this. This is an isosceles trapezoid. If I ask it to look at that segment there and that segment there, okay, it is isosceles, so you're seeing that those two lengths are 5.38 down here, right? Once I change this thing from being isosceles to just a general trapezoid, you now see that those two lengths are incongruent, okay? They differ now. Still a trapezoid though, right? Okay? So just something to think about. It's not a property you can always use based off of just any general trapezoid. It has to be an isosceles one, okay? And you can start to see, if that's isosceles again, 3.16, 3.16, and you're seeing then you still have those two lengths being the same, okay? So that's nice. This is another definition, okay? Defining a particular segment that exists inside every single trapezoid, and it's referred to as the median. Okay, and we're going to actually there's two names for this thing. Your textbook, Math Excel, for the most part uses median, but I do pick questions from other texts, and other texts might use midsegment. Okay, in of course exam, the author of that might write it as a median, or they might write it as midsegment. Okay, so we got to know that we've got synonyms here, right? I like to call it a midsegment because it reminds me of the midsegment of a triangle, and it actually has very similar properties that midsegments of triangles have. Okay, that's why a lot of textbooks use the word midsegment, is because of the relationship between midsegments of trapezoids and midsegments of triangles. Now, if you are talking about this red segment up there, you have to make sure that you tag on the phrase of a trapezoid, okay? Because median exists for a triangle and it exists for a trapezoid. Does that make sense? Or if I talk about midsegments, those existed for triangles and they exist for trapezoids. Okay? So if I just say median, you don't know what shape I'm talking about. Okay? But if I say median of a triangle, now you know. If I say midsegment of a triangle, now you know. Say midsegment of a trapezoid, now you know, right? Okay, so that is very, very important that we use that phrase there. Okay, so the median by definition, or the midsegment by definition, is the segment that joins the midpoints of the legs. So again, the legs are the non-parallel sides. I go find their midpoints on both of them, and then I connect them. Okay. Now I want to draw a comparison back to what we have done in dealing with triangles. So let me open another thing here. If I deal with, let's say, that triangle there, and I find the midpoint of that segment and the midpoint of that segment, and then I connect them. That blue segment is the midsegment of the triangle, right? Okay. Do you guys remember talking about the slope of that segment and that segment being the same? Okay. And you can see no matter where I move F, no matter where I move G, okay, those slopes are going to be the same, right? So that was a fact about midsegments, is that they have equal slopes. They're parallel, okay, for triangles. Now, if I do this, if I ask the length of this segment and the length of that segment, okay, so the length of the blue segment is 3.74, the length of that third side is 7.28. So if I take n, let's do it this way. If I take q and divide it by n, I get 0.5, right? So what that's saying is that this blue segment is 1/2 this side here. You remember talking about that kind of stuff? And that 0.5, no matter where I draw my triangle, does that 0.5 over there on the left-hand side ever change? No. The values that are getting compared change, right? The n and the q, they change. Okay? The slopes change, but the slopes relationship is always the same, right? So with mid-segments of triangles, we had parallelism with the mid-segment and the third side. And we also had the relationship that the mid-segment was half the length of the third side. So what I'm going to do is I'm going to take this triangle. I'm just going to kind of redraw it over here just a little bit smaller just to get it out of the way. Now I'm going to take and deal with, let's say I just cut the top triangle off here. So I would have something that looks like this. Okay? So I got that trapezoid, right? That's what I get when I just look maybe basically at this shape down here, cut the top off. Okay? Can we find the mid-segment of that trapezoid by finding that midpoint and that midpoint? That make sense? If I connect them, I should get that red segment, right? What do you think the argument is about that segment compared to that one and that one? Yeah, they're parallel, right? Does that make sense? Okay. And the reason I introduced that with the triangles is because hopefully by now we know that about triangles. So now we can make a similar understanding or similar relationship with the trapezoid. Okay. So the mid-segment of a trapezoid is always going to be parallel to the bases. Okay? Always going to be parallel to the bases. Now, I didn't construct this well enough to be able to move these points and shit because that's no longer a trapezoid. So I didn't construct this well enough to show that we can move this around like we did the triangle. But those will always be parallel. Okay? Those three segments. Let's do this. Let's say, because there's another component to this, but it's not as easy to recognize as it was with the triangle. These are the two components. This is the theorem that we're trying to address here. The first component we just talked about. The median or the mid-segment is parallel to both bases. And the second component is actually a formula. And this is where as you move through advanced math classes, some of your formulas are presented verbally to you. Okay? They're not presented as a mathematical representation. Here it's just in everyday English, right? It says that the median has a length equal to the average of the base lengths. Okay? Well, how many bases do you have in any trapezoid? You have 2, right? Okay. So this is maybe base 1 up here. This is base 2 right there, right? Does that make sense? And those could be flip-flop. Doesn't matter which one's base 1, base 2. But what they're saying here is that this red segment's length is equal to the average of the base lengths. Well, how do you find an average of something? Add them up and divide by how many you have, right? So when I add these up, I get B1 plus B2 over 2. Okay, and that may be the way that it's presented sometimes in some textbooks. I'm going to write this way because of how we're going to use this in other chapters. I'm going to factor out the 1/2 that is here and write this as B1 plus B2. Okay, and that is the formula, 1/2. The sum of B1 plus B2, that's the formula that's being expressed there in bullet number 2. Okay? Now, kind of show you where this is going to be useful for us. Obviously, it's not an extremely hard formula, but it is very impactful in what we do later on. You guys ever remember seeing this formula from previous grades, like 7th or 8th grade? 1/2 H B1 plus B2. Anybody remember seeing that? Last class said they saw it before. Okay, that is the area formula for a trapezoid. Okay, where H is essentially that distance right there. Okay, but if I look at this, this is just a number, that's just a number, and B1 plus B2 is just a number. So you have three numbers being multiplied together, right? Three numbers being multiplied together, you can always reposition them using the associative property and the commutative property, right? Okay, so I'm going to rewrite it this way. H times 1/2 times B1 plus B2. And now using the associative property, I hope you recognize that if I put brackets around that thing in the red is the length of the midsegment, right? 1/2 sum B1 plus B2. So eventually, now you don't need to know area formula right now, but eventually, in the coming chapters, when we deal with area formulas, we're going to need that 1/2 B1 plus B2 digits. And I'm going to refer to it, hey, find the midsegment here, okay? So the formula for the area of trapezoid a lot of times is referred to as the midsegment times the height, okay? Midsegment of trapezoid times the height, or the altitude, another word for height. Okay, so what I'm trying to show you here is not that we're going to use that directly right now, this formula, but I want you to open your eyes to the importance of learning it now so that later on things are easy. Okay, now I want to prove this formula. Okay, I want to prove in the next slide it shows it using A, B, and C, D instead of B1 and B2. But I want to show you using a little bit of coordinate geometry on how we can do this. Okay? So don't draw this, and I'll tell you when you can start drawing stuff. So I want you to have this in your notes as well. But right now, I've just got some random trapezoid. Would you agree that random trapezoid is probably going to have some really cruddy ordered pairs for X, Y, Z, and W? Okay? Now, what I want you guys to understand, you can pull from 7th and 8th grade math here, is that we should be able to take that orange figure and slide it. Okay, move it left, right, up, and down any way we want to, right? And if I move that thing any way I want to, do I shrink it or enlarge it at all? If I'm just sliding left and right, up and down? No. So the distance between X and Y here, and in the image right now, and then when I move it, wherever I move it to, is that distance between X and Y going to be the same? Yes. Okay. When we use the left and right movements and up and down movements, we call those rigid motions. Okay. And basically, I think the reason we call them rigid is because that shape doesn't change. Okay. If you have somebody, if you have a parent that's rigid, they don't bend their rules or anything for you, right? Okay. They're rigid. You know the way they do things, and they're not going to change. Okay. That's the same idea here. We're talking about rigid motion. We're going to do a motion to this thing that doesn't change any distances. Okay. When we do translations, that's what the left and right, up and down movements are called, or rotations, they're rigid motions and lengths are preserved. They're saved. They do not change. Okay. So, dealing with showing the fact that that midsegment that we're going to put in here in a minute is half the sum of the bases is really hard with that shape because the ordered pairs are really ugly. But if we understand the idea of translations and rotations, we should be able to take that shape right there and move it. Now, I just have a movement of rotations, but I should be able to move it to now be positioned close to the origin, right? When I say close to the origin, this one I actually put a vertex on the origin, but generally speaking, it doesn't always have to be on the origin, but we like to have points on axes and points on origins if we can. It makes the algebra a little bit easier. But would you agree that that trapezoid is going to have the exact same properties as the other trapezoid? Yeah. Okay. So hopefully what we're seeing here, or what we're recognizing is this, what we learn about this trapezoid here is going to be true essentially for any other trapezoid. Because the idea of the rotation says we can put it anywhere else in the coordinate plane. But we also have the idea, what we talked about yesterday, is that we're going to choose ordered pairs here that are arbitrary. Okay, so if I get back to this, we've got some ordered pairs here that are pretty arbitrary. Would you agree with that? So the conjunction of arbitrary ordered pairs and the idea of rotations and translations, saving distances, preserving them, allows us to prove something about this trapezoid and then convey that over to all possible trapezoids that you could ever create. Okay? So that's what I want you to start writing down. Okay? Draw that picture with those ordered pairs, and we're going to prove then the formula for distance of that or length of that mid-segment. The end, of course, is the end. I don't know if they're going to ask you, because our questions are different every year. I don't know if they're going to ask you to prove something using coordinate geometry. Okay, kind of the way we are. It's very feasible that they could do that. That's why we're doing this. But they will inevitably probably show you at least one problem that has a diagram like this. You have to interpret and be able to read that diagram. Okay, if you've ever taken the ACT, generally the ACT will have a question on there that you have to be able to read a diagram like this, where we just have arbitrary values for your ordered pairs. Okay, and what we learn about that trapezoid, because they're arbitrary values, will be the same that we learn about that trapezoid, same as that trapezoid, same as that one, same as that one. Okay, and we can change all these trapezoids. We can make these lengths different. Okay, but what we learn about one of them is going to be consistent and true about all of them because of the way we've chosen our ordered pairs. Okay? So, as we move on, let's kind of talk about how we develop a mid-segment. Okay? In creating a mid-segment, we need the midpoint of the legs, right? Would you guys agree that that side there and that side there are the legs? Okay? So how do I find the midpoint of that leg? How do I find, a spot here in the middle based on its ordered pair of that segment? What do I do with my x values of z and w? Midpoints. How do we find midpoints, folks? If this was like 6 and this was 4, what do you do with that 6 and that 0? Careful. Add them and divide by 2, right? It's the average of the x's. So right now, my x's are b and 0. Add those, divide by 2. So you get b over 2, right? Okay. Do I do the same thing with my y's? So we get c over 2. Okay. So the ordered pair right now for the midpoint, for that point right there, is b over 2, comma, c over 2. Can we do the same thing over here? Okay. So now, looking at these two ordered pairs, I'd take the average of the x's, a plus d divided by 2, and the average of the y's, right? So c over 2. Okay, now I'm going to put that segment in right there. And that's your mid-segment, right? How many points do you need to find the length of a segment? You need 2. You need the starting point and the ending point, right? You need both endpoints to find the length. And we know that length, and there's actually 2 ways. There's an easy way and a more maybe formula-based way that you guys are familiar with to find the length of that blue segment. Would you agree that the blue segment is going to be found by using this formula? Okay, now let's think about this, because it's not extremely difficult here. If I look at that blue segment, that's x2, right? And it doesn't really matter, but I'm going to let that be x2 because it's further to the right than x1. Okay, so let's subtract those. Well, if I subtract those, I got a plus d over 2 minus b over 2. That would be the difference in x's, right? I'm going to square that. I'm I'm going to then add to that the difference in y's. Well, if I do the difference in my y's, what's c over 2 minus c over 2? 0. What's 0 squared? 0. Okay? So that's really nice. Okay? So now you will really only have, just erase it, you only have that, right? What's this power of 2 and this square root going to do? Cancel out. So now you have distance of this blue segment to be a plus d over 2 minus b over 2, right? Are those the same denominator? So let's write it this way. For the same denominator, we should be able to just add the exponent, or sorry, add the numerators, right? So I should have a plus d minus b over 2. Now I'm going to write it in a more convenient way. I'm going to, for us, I'm going to factor the 1/2 out. And it gives me a plus d minus b. And that is the length, that is the distance of that blue dotted line. Is that okay with everybody? Okay? That doesn't tell me anything. That doesn't tell me anything about how this thing relates to the bases. Because the bases we haven't talked about yet. We haven't found those lengths. So let's find the length of this base right here. We use the distance formula again. Okay? I'm going to take that distance, or that x value, minus that x value, right? So d minus b. Oh. D minus b squared plus difference in my y's, c minus c squared. Well, what's c minus c going to give me? 0. It's 0 squared. 0. So let's just really get rid of that. What's going to happen with that square root and that power 2? Cancel. So did we just find the distance of that segment right there to be d minus b? Okay. Let's come down and do the same thing for this distance here, w to x. If I do that distance, okay, this one's going to be a lot easier. I'm going to take the x value, a, and 0, and subtract those. So it gives me a, right? Square that. And then I'm going to get 0 minus 0, which gives me 0. 0 squared is 0. So really, I only have the square root of a squared, which just gives me what? Just gives me a, right? Okay. Now let's look at these parts and compare back to what we found for the mid-segment. If I take that and that, would you agree that the a is right there and the d minus b is right there? And what are we doing with that a and that d minus b with that symbol right there? Add them together. So does that prove to you that that red equation, 1/2 the sum of a plus d minus b, is taking the distance of the top base and adding to it the distance of the bottom base and multiplying by 1/2?
Yes.
Okay. So the reason we do that, and now we can change a, b, c, d to any numbers that we want to. Okay. As long as we maintain this shape to be a trapezoid, that mid-segment's length will be exactly 1/2 the sum of a plus d minus b. Okay. Which is saying it's the sum, it's half the sum of the bases. Does that make sense?
Yes.
Okay. So that's where a lot of your formulas come from. Okay. When we've dealt with this formula, we've proven that in the past. We might come back to it, prove it again. That usually might be something the end of course exam kind of addresses because of how common that formula is. But a lot of your formulas that you know, and a lot of the formulas that you're going to learn in this course, come from kind of implanting a generic shape, maintaining, it's trapezoids, we've got to maintain one set of parallel sides. But implanting that in the coordinate plane with arbitrary vertices and working through some relationships. And knowing our algebra and how that algebra works, we can come up with those relationships and recognize that that should be true then for all trapezoids. Is that all right? Okay. There's an assignment in Math Excel. It's called 6.6 New. Okay. So if you're a person that already worked through and done 6.6, you still have to do this one. Okay. So that is due tomorrow, and you guys may go to lunch.